Imagine a glass of water on a sunny day. The sunlight dances on the surface, creating a shimmering effect that catches your eye. A straw rests inside. When you look at the straw from the side, something strange happens. The straw, which you know to be straight, appears to be bent or even broken. The straw appears broken at the water's surface. Why does this happen? What causes this curious visual trickery? The answer lies in the magic of light and a phenomenon called refraction. Refraction is the bending of light as it passes from one medium to another. Light travels in straight lines, but when it passes from one medium to another, like from air to water, it changes direction. This change in direction is due to the difference in the speed of light in different materials. This bending of light is what causes the straw to look broken. The light rays coming from the part of the straw submerged in water bend as they exit the water and enter the air, creating the illusion of a break. It's an optical illusion created by light's journey through different materials. This simple phenomenon can be observed in many everyday situations, not just with a straw in water. This simple observation opens a window into the fascinating world of light and its interactions with matter. By understanding refraction, we gain insight into how lenses work, how rainbows form, and even how our eyes perceive the world around us. The next time you see a straw in a glass of water, take a moment to appreciate the complex dance of light that creates this watery illusion. Every material has a property called its refractive index. This is a fundamental characteristic that determines how light behaves when it encounters different substances. This index measures how much a material can slow down light. Essentially, it tells us how fast or slow light will travel through a given medium compared to its speed in a vacuum. Think of light as a car traveling on a highway. On a smooth open road, the car can travel at its maximum speed, just like light in a vacuum. When it enters a material with a higher refractive index, it's like hitting a patch of rough road. The car or light has to slow down because the conditions have changed. The car slows down and changes direction. Similarly, light not only slows down, but also bends when it enters a denser medium. The higher the refractive index of a material, the more it slows down light and the more light bends. This bending effect is crucial in many optical applications, from lenses to fiber optics. This bending of light at the boundary between two materials is what we call refraction. Refraction is responsible for many everyday phenomena, such as the apparent bending of a straw in a glass of water or the focusing of light in a camera lens. Different materials have different refractive indices. This means they bend light to varying degrees. Water has a higher refractive index than air, which is why the straw appears broken in our earlier example. Glass has an even higher refractive index than water. This is why lenses made of glass can bend light so effectively. They can focus light to a point, creating magnified images or correcting vision problems. One of the most spectacular demonstrations of light's interaction with matter is the rainbow. Rainbows are formed through a combination of refraction, reflection, and a phenomenon called dispersion. Dispersion occurs because different colors of light travel at slightly different speeds through a medium. When white light, which contains all colors, passes through a prism, the different colors are bent at different angles. This separation of colors creates the beautiful spectrum of a rainbow. Absorbed and transformed. Light's energy exchange. When light encounters matter, it's not always reflected or transmitted. Sometimes it's absorbed. Think of a black shirt on a sunny day. The shirt absorbs most of the sunlight, converting it into heat energy, which is why it feels warmer than a white shirt. Different materials absorb different wavelengths of light. This selective absorption is what gives objects their color. The color we see is the color of light that is reflected, not absorbed. The energy within. Light's vibrant spectrum. Light is not only a wave, but also a stream of energy packets called photons. The energy of a photon is directly related to its frequency. High-frequency light, like blue or violet light, carries more energy than low-frequency light, like red or orange light. This energy difference is why ultraviolet UV radiation, which has a higher frequency than visible light, can be harmful to our skin. It carries enough energy to damage our cells. Bending the rules, light's surprising detour. Light travels in straight lines, right? Well, not always. Under certain conditions, light can bend around obstacles, a phenomenon known as diffraction. Diffraction occurs when light waves encounter an obstacle or an opening that is comparable in size to their wavelength. The waves spread out, bending around the edges of the obstacle. This effect is more pronounced with longer wavelengths, like those of sound waves, which is why we can hear around corners. Light's marvelous journey, a universe illuminated. From the bending of light in a glass of water to the dazzling colors of a rainbow, light's interactions with matter reveal a universe of wonder and complexity. Refraction, dispersion, absorption, and diffraction are just a few of the ways light interacts with the world around us. These interactions allow us to see, to understand the cosmos, and to develop technologies that have transformed our lives. Beyond the visible, exploring light's hidden realms, light is more than what meets the eye. The light we see with our eyes is only a tiny fraction of the electromagnetic spectrum. This spectrum encompasses a vast range of wavelengths, each revealing unique aspects of our universe. Beyond the visible spectrum lie radio waves, microwaves, infrared radiation, ultraviolet radiation, each with its own distinct properties and uses, X-rays and gamma rays. These high-energy waves can penetrate through objects, revealing hidden structures and phenomena. These invisible forms of light carry information about the universe, acting as messengers from the cosmos. From the faint whispers of the Big Bang, captured in the cosmic microwave background radiation, to the energetic emissions of distant galaxies, each type of light tells a different story. Scientists use telescopes and detectors to capture and study these invisible forms of light, employing advanced technology to decode the messages they carry. By analyzing this data, astronomers expand our understanding of the cosmos, uncovering the mysteries of its origin, structure, and evolution. The study of light, in all its forms, continues to illuminate the hidden realms of our universe, pushing the boundaries of human knowledge. Light in our lives, from vision to technology. Light is not just a scientific curiosity, it's fundamental to our existence. Our vision relies on light entering our eyes and being absorbed by photoreceptor cells in the retina. Beyond vision, light plays a vital role in countless technologies. Fiber optic cables transmit data at the speed of light, connecting the world through the internet. Lasers, which produce highly focused beams of light, are used in medicine, manufacturing, and communications. The enduring mystery unraveling light's secrets. Despite centuries of study, light continues to hold mysteries that intrigue scientists. The dual nature of light, its ability to behave as both a wave and a particle, is a profound concept with far-reaching implications. As we delve deeper into the quantum world, our understanding of light continues to evolve. The study of light is not just about illuminating the world around us, it's about illuminating the very nature of reality itself.